It's great to see such a good turnout on in these difficult times. Firstly, if you could make sure two things: make sure all your electronic devices are switched off or silent, and no coughing during the presentation, please. And if there's a fire, we should leave the building. There's quite a good pub around the corner. Tom Lennon, our speaker tonight, has worked for BRE for over 35 years. He was responsible for the programme of full-scale fire tests carried out at BRE's large-scale test facility at Cardington on steel, concrete and timber frame buildings. Mr. Lennon has extensive experience of the structural Eurocodes. He was a prominent member of the British Standards Committee, BS 52532, is that right? Yeah. The mirror group for the free part of EC1. Gosh, there's a lot of letters in here. I think I'll just pass over to Tom.
Fine, yeah, fine. Thank you, Ivor.
The floor is yours.
Okay, well, good evening, ladies and gentlemen, and thank you very much for this invitation to come and speak to you. I'm not quite sure how it arose, to be honest, but nevertheless, I'm here, and I hope you'll find what I've got to say of interest. The first thing, in terms of the introduction, other than my micro CV, which I think was aimed at the European community in terms of getting on the project team for EC2 fire part, so it was the closest I had. I work in the building research establishment, as was, and I've worked there for a long time, and I deal with fire issues. So I'm not a specialist in terms of tunnels. I'm not a specialist in terms of even testing tunnels. It's one aspect of the work we do. So we cover fire investigation, consultancy, research, assessment, all sorts of things to do with fire. But over the years, I've also been involved in looking into research into the fire performance of concrete in general, and that has led ultimately to being involved in fire testing for tunnel linings. So the presentation tonight is going to cover really two aspects of that work. The first is a basic background to some of the important parameters that influence the performance of tunnel linings in fire, particularly in terms of spalling of concrete. And the second part will be focused specifically on tunnels in terms of the types of test and assessment procedures we use for common tests. I don't know what the normal format is in terms of these meetings, but I'm quite happy if you want to have people interject or ask questions as I go along. Alternatively, if you want to hold them and we'll deal with any issues raised at the end, it's entirely up to you. But if you do want to any clarification, just stick your hand up and I'll stop. Okay? So what we're going to talk about, a little bit of history, first of all, and the history will help define the reasons why we do things the way we do at the moment. Talk about particularly explosive spalling, which is a major issue in terms of performance of tunnel linings, and there's been a subject for research in the fire industry for quite some time. Look at the procedures for test and assessment. Look at some of the commercial programs we've done in terms of testing. I've mentioned here Crossrail. Crossrail, we were heavily involved in lots of tests for different parts of the Crossrail project, and we're now moving on to HS2 as the large infrastructure project, and in fact we've been testing this week in that area. So if you've got any specific questions related to that, I won't answer them. So why does it matter? Why do we need to do fire testing? Why is it important? I think if you do a quick Google search of fires in tunnels, you'll find lots of information on major fires in tunnels, including fires that have led to significant loss of life and extensive economic costs. Being such important infrastructure projects, the knock-on effects are considerable. So there's been a lot of structural damage, consequential losses and loss of life. So it needs to be considered, it needs to be thought about, it needs to be planned for, and where necessary, steps need to be taken to try and mitigate the risk. So I've got some instructions here. This next one says just read the slide. So we'll go on and we'll just read the slide because hopefully it's self-explanatory. So this is a bit of background. So we're talking about spalling. In terms of structural damage, we're particularly interested in what you call explosive spalling, which is pretty much what it says in terms of losing large sections of the lining in an aggressive manner. So we look at the parameters that influence spalling, and a consideration of the literature and experience gained over the course of many years, in my case, suggests that spalling is more likely in the event of high moisture content, which is something related to the buildings, not just tunnels, high concrete strength, a rapid increase in temperature or high levels of restraint or applied load, or any combination of these factors. So these are the main parameters that govern spalling. And in some cases, in terms of design, you don't need to do anything. Because if you use standard design procedures for buildings, particularly, there's an implicit consideration that spalling's taken into account in the levels of cover you specify in terms of the minimum dimensions for your elements. But there are times when you do need to take some steps. So one route is to consider a risk-based approach and to look at the parameters that influence spalling, and if you have one or more of these parameters in your project, then perhaps you need to consider doing something. It might be testing, it might be protection. There are lots of options. So what are the potential solutions? The obvious one, the one that will come up time and time again tonight, is the inclusion of polypropylene fibres in the mix, which has been around for quite a number of years now. Alternatively, you can use fire barriers, you can use boards, you can use sprays. Mixed design to reduce the tendency for explosive spalling, or you can attempt to control the environmental conditions, or try and ensure that you don't have a fire in the first place, which is probably the best procedure. So again, a bit of history, and not specific to tunnels, but I think it's all relevant in terms of the performance of concrete in fire, and then when we come on to look at fires in tunnels, it's all relevant. So I was involved early on in terms of looking at high-strength concrete columns for buildings. It started to be used. I know there were a couple of projects when they were building Canary Wharf where they used high-strength concrete for the lower floors of the building, which meant that you could use more slender sections than you otherwise would have been able to. And the problem is with high-strength concrete, with low porosity, low permeability, high density, is that you have a build-up of stress and nowhere for that stress to be relieved in the case of a fire. So there are particular factors with high-strength concrete that make it susceptible to spalling. These were understood to a certain extent in the early days. Poor pressure and thermal stress were the most important considerations, and when we looked at this in terms of the use of polypropylene fibres, this was a fairly innovative use of a material that was generally used to prevent shrinkage cracking in slabs. So it was a new application of an existing technology. So we carried out a research project for the at the time for the UK government, for whatever the department was called at that point, where we subjected a number of columns to axial load using a 500-ton compression machine and a fire exposure provided by a portable gas-fired furnace. In this case, the fire exposure was a standard fire exposure because we were looking at buildings. So the first series of tests were on unreinforced columns, 1.5 metres high, 200 by 200, so fairly typical slenderness ratios for columns. Looked at two different strengths, C85 and C105 with microsilica, limestone aggregate, a variation of some with and without polypropylene fibres, and a difference in terms of the load applied, so either 40% or 60% of the ultimate load capacity applied. This is a picture showing the basic test setup, which hasn't changed much over the years. This particular furnace here, gas-fired furnace, was designed to fit in between the screw jacks of a 500-ton compression machine, which means you can load it at the same time as heating it, which is quite useful. So the results from the unreinforced columns, I'd like to show you lots of pictures, but most of them ended up in a dustpan on the lab floor, actually collapsed, so before the end of the exposure. One of the things that became very important, became very apparent from these tests is the impact of load ratio. Very, very important. So the 60% loaded ones, none of the columns survived the test, regardless of whether you included polypropylene fibres or not. So it's not always the be-all and end-all in terms of a solution to all your problems. Other things need to be taken into consideration. So only 4 specimens of 30 remained intact at the end of the test. Sorry, yes, please.
How do you differentiate the first crack and the collapse in this case?
If we go back to the...
How do you define collapse in case of the fire?
In this case, collapse was quite easy to define. It was literally ended up sweeping concrete off the floor. So you had you would define it as being an inability to support the applied load. But in point of fact, it was a complete collapse of the columns. So of these, sorry, let me go one more forward. Of these tests, and remember these were unreinforced, so just plain concrete. Only 4 specimens out of 30 were actually columns at the end of the project. Of these, three of the 4 that survived included polypropylene fibres. None of the specimens under 60% load survived the test, regardless of whether there was polypropylene fibres there or not. So we found that polypropylene fibres can reduce, delay or eliminate spalling in high-grade concrete. This was a critical finding. But the load ratio is also very important. So this is of the one that didn't have polypropylene fibres that survived. The only one is this one here, which is 100 Newton concrete, and this one here, which has polypropylene fibres and microsilica, and you can see the difference in the behaviour. But as I say, most of these, there was nothing to compare, no photographs, because there was nothing left. So we then went on for a more practical case to look at reinforced columns. So the same size, same setup. We looked at different strengths, so including normal strength concrete as a control, C45, C65, C85 and C105, different polypropylene fibre dosages, fixed moisture content, and a compression load which is kind of more representative of reality of a third of the ultimate load capacity. In this case, we had a better performance in terms of preventing collapse, and this slide here shows effectively we've got a C85 mix here without polypropylene fibres, and you can obviously see the exposed reinforcement. We've got a C85 mix here with a 3 kilogram per metre cubed dosage, and one with effectively a double dosage here, not too much difference here. And what's important, I think you people in here who know much more than I do about mix design, what you want is not a specific level of fibre. What you want is the lowest level of fibre you can get to give you your performance, because there are knock-on effects in terms of strength, in terms of workability, if you end up with too much polypropylene in the mix. I'm sure, as you say, I'm sure you know more than I do on that score. So, no collapse in any of the situations. Residual strengths were measured, very important, and when we come to look at tunnel linings in terms of the criteria for assessment, residual strength is very, very important. So residual strengths here between 55% and 75% of the ultimate load capacity, so there's a clear reduction, but some capacity remains. Larger loss in residual strength for those columns not containing fibres, and a loss in residual strength increases with increasing grade of concrete. We produced a long time ago now, myself and my colleague at the time, Nigel Clayton. Do you remember Nigel? Anybody? Charles, do you remember Nigel Clayton? No? Okay, very, very good guy and very knowledgeable. Not quite sure where he is now, but some guidance document produced when we were still in the civil service, and it was easy to get hold of. The work we did was used as input to the European Concrete Building Project. Does anybody in the room know of Cardington, the work that was on in Cardington in terms of the large-scale test facility? Okay, we had we're fortunate enough to have an 8-storey steel frame building, a 7-storey concrete building, and a 6-storey timber building that people were allowed to play with, and I was allowed to set fire to, which was quite good. But the work in terms of the columns there was informing decisions about the design of the European concrete building. We carried out a fire test, a natural fire test on the ground floor in a compartment 15 metres by 15 metres by 4.25 metres high. And the test area included 1 completely exposed internal column and 8 partially exposed columns at the boundaries of the test compartment. You can see here, before the fire, you've got the internal column here on the plinth, and we were concerned, because this was high-strength concrete, about the effects of spalling, and it might actually collapse the building. So we built a frame around here, to protect the column. In the event, we needn't have worried. We didn't have any spalling of any significance on the high-strength columns. What you might just be able to see, we did have very extensive spalling of a normal strength concrete on the slab here, and that's the exposed rebar that you can see there. So with high-strength concrete, with the polypropylene fibres, no spalling. With normal strength concrete and no fibres, we had extensive spalling of the slab. So it's not just high-strength concrete that's the problem. So afterwards, some localised cracking, some edge spalling, really in the cooling phase, but nothing significant and no structural damage arising. So that's the first half in terms of the background and the parameters and the things that we learned. We then used this experience to move on and look at the effect on tunnel linings. So explosive spalling is something that's a specific worry for tunnels, because you have all the parameters within a tunnel which impact on explosive spalling and tend to increase the likelihood of explosive spalling occurring in a fire. So first of all, you have often have a hydrocarbon, maybe petrol tankers within the tunnel. So the fuel load is very high, rapid rates of temperature rise. You have significant restraint against thermal expansion in a tunnel, in most tunnel situations. And you have often high-strength concrete, whether you designed it as such or not. So you have this, what I would term a perfect storm in terms of the risk parameters that influence explosive spalling. So for that reason, something has to be done. As I mentioned before, there's plenty of examples where we've had fires and there's been significant damage and loss of life. So, given the nature of tunnel fires and the form of construction used in tunnels, this is kind of a personal opinion, but I think it's very important. It's essential to ensure that the proposed design solution is capable of resisting a hydrocarbon fire while under load. So load is important, and the temperature rise is very important. There's currently no standardised approach for testing and approval of tunnel lining segments in relation to fire performance, and there's a good reason for that, because tunnels are different, the specific circumstances vary from case to case, so to have too much of a prescriptive approach would be a mistake, but it also means that, which is the best approach, which way do you go? So some attempts have been made, this ridiculous acronym FNARC, European Federation of National... I'm not even going to do it. But they did produce some guidance. I don't know if anybody's familiar with the FNARC organisation. This was produced some years ago, 2006, a specification and guidelines for testing of passive fire protection for concrete tunnel lining. So it's an attempt made to standardise, to codify procedures for testing. One of the most important aspects of looking at fire performance of tunnels is to model the fire exposure in some way or another. And there are a number of different fire curves, which you can see here, ranging from, we have the normal standard fire curve here, We have on the other extreme the RWS curve, where you're talking temperatures up to around 1360, I think, which is a bit ridiculous if you ask me. What we've focused on largely is the Eureka curve, which is here, I believe, where you're up to 1200 degrees after about 5 minutes, hold that for 60 minutes and then come down in the cooling phase, which is a severe fire exposure but fairly representative of a hydrocarbon fire in reality. So BRE started out, when I say BRE, it is largely me actually. I think I'm the only person who's been involved in this area for several decades now, but nevertheless, we've provided specialist fire test services for a number of high-profile tunnel projects. Initially, these were just at the specification of the client. So we didn't say we're going to do this, we're going to do that. People came to us, they said, can you do this? Can you follow this curve? Can you load it? And eventually we did some work, initially for Channel Tunnel Rail Link in the early years. We did some work for Heathrow T5 Tunnel, Terminal 5, Hindhead Road Tunnel. There's been a number of cases where people have maybe an innovative mix design that they want to assess, and they come to us and they look for a specific fire exposure. We can do that. We're flexible. The expertise derived from these projects provided input to the specification for fire testing of sprayed concrete linings for the Crossrail project. I'm sure many of you have been involved in Crossrail. You may know that in terms of fire performance, there were two different specifications, one for the sprayed concrete linings and one for the precast. I'm not quite sure the fire knows the difference between a sprayed concrete lining and a precast, so I'm not quite sure why you need two different specifications, but we can maybe debate that. So commercial testing, loaded panel sections using the 500-ton compression machine we saw earlier, hydrocarbon fire exposure at one face of the panel, and we generally use 1.5 metre high by 750 wide by 350 odd specimens. And this is to fit in between the screw jacks of the machine, so it's practical reasons for the geometry. But it's large enough, I think, to simulate effectively the stress conditions you'd have in reality. I've seen this slide all over the place actually, but this is a very good example of a with and without in terms of both subject to exactly the same fire exposure, one obviously with polypropylene fibres, one without, and you can see the extent of the explosive spalling there. Our clients don't like explosive spalling. I absolutely hate it, because when this happens, what happens is my furnace gets wrecked and we have to reline the furnace, which costs a lot of money. So for me, I'm always very, very happy if we can do work for clients and we don't get any explosive spalling. But occasionally it does happen and we have to deal with it, and that's what it looks like. Again, you can see the depth of spalling here in terms of exposing the main reinforcement, so obviously having a major impact on the structural performance. And you can see there the various levels of spalling, from the deep one here, some extensive surface spalling, to here really fairly superficial spalling of the surface. So, Crossrail, two different specifications I've mentioned for sprayed concrete linings and precast tunnels. Both the sprayed concrete linings and the precast segments require the use of the Eureka curve. The sprayed concrete linings in this case had an applied load of 5 megapascals. That's certainly changed on the HS2 specification now, but we can accommodate other values. For the sprayed concrete linings, there's a possibility of doing small scale to look at maybe the preliminary mix design to see if it's likely to spool before you go on to do the larger test samples. It's not, I don't think it's mandatory, but if you've got any questions, it's better to find out if you've got any problems at the early stages rather than commissioning the large-scale panels. The performance criteria, very, very important here, is based on the depth of spalling. So there's normally a requirement to limit the depth of spalling. I've seen some of the earlier specifications which called for no spalling, and I'm not quite sure why that's required. I think what matters is not whether it spalls or not, but whether you have an impact on the structural performance. So I think this is more sensible than saying it shouldn't spall. We look at the temperature rise within the slab. I'll show you what we do there in a minute, but in terms of the temperature distribution through the slab, what's often important for the splayed concrete linings is the impact on the waterproof material, which may have a certain melting point, so you've got to limit that to a certain value. And importantly, the residual strength of heated concrete. So once we've actually done the test, we do take some cores, which I'll show you some pictures. We do a core log and a strength profile through the depth. So that's a Eureka curve. Sorry, yes?
Question regarding the waterproof material. If you're assuming a precast lining and you're expecting a spalling failure over there, and there's the gasket that's over there, so will that melt first and the water will vaporize in that? Or the one in the concrete will vaporize and cause spalling first?
I think it depends on the design, to be honest with you. I mean, we are measuring temperatures through the depth, and we're measuring the extent of spalling. The actual impact of what we're measuring depends on the thickness of the lining, depends on the thickness of the precast unit, the level at which the waterproof membrane is. So I think it's specific to the design. So. But yeah, as long as we know what the temperature distribution is, then we can make decisions. And it also depends on the constituent materials, which vary in terms of their melting temperature. What this shows here, it's quite important actually, is to get to 1200 degrees in 5 minutes is quite a challenge in terms of furnace, in terms of thermal dynamics, to be honest with you. And I think that's accepted in the specification. In the early stages, you have a tolerance level, but within, as you go along, you need that tolerance reduces. So when you're in this phase here, you have to be very, very close to 1200. In the work that we do, we have quite a close correlation, so we don't really go too much outside of this main curve here. It's actually impossible, if you think about this, we're heating something, a small volume, to 1200 degrees, to then, from 60 minutes to 170 minutes, get back to ambient temperature. It's not possible, and you need to have this under load constantly. So, although here it looks like there's no tolerance on the cooling phase, in reality, I think you basically have to get from here to here in as short a period as you can and get as close as you can to this curve. What we actually find with the dynamics of the furnace is that from here to about 110 minutes, we can follow this curve almost exactly. When you get down to 300 odd degrees, you can't actually achieve that. We turn the furnace off, switch it off, and you eventually end up somewhere down here. But in terms of the behaviour of the panel and the performance criteria, it's irrelevant, but again, we can discuss that. So this was from the Crossrail specification and shows on here we see what are small cylinders as a sort of pre-test, preliminary test. I actually don't favour this anymore. I think it's better to do a panel test, but a smaller panel. And these are the larger panels showing the heated area and the overall geometry of the section. This is showing the small-scale test, which I haven't done for a long, long time, but a cylinder here, which is, it's not really under load, but it's restrained. So we've got basically a bar that runs through there and a plate that we tighten up. And we also subject this, take it straight out of the furnace, and stick some water on it and look at the effect of cooling, which can be significant sort of thermal shock you get here, and that's the end result. And that's on a panel that didn't spall at all. So the thermocouples, there's a lot of work goes into designing these systems, and a lot of the time it's based on finite element modelling, CFD modelling to look at temperature distributions, and the models can be validated with a good idea of what the temperature distribution is through the concrete. The models will only work if there's no spalling. If you get spalling, it's very difficult, almost impossible to model. So what we have is various distribution through the panel, and then at specific distances from the surface, we have thermocouples through the depth at each location, which gives you a good idea of the temperature distribution throughout the panel. So we have to place these thermocouples. This is from the Crossrail, one of the Crossrail projects, where we have to visit the sites, and before they're cast, we have to install the thermocouples. We have to make sure that they're in the right positions, and that they're not affected once in this case, the panels are either sprayed or poured. It's also very important to protect them so that when they arrive at our laboratory, they're working, they're in good order, and we install the thermocouples ourselves on site, so the blame for that if it doesn't work is down to us. This is, you see the surface of these are sprayed concrete. Obviously the precast panels tend to be a little bit smoother. The specifications in general, we're testing panels which have been subject to exactly the same curing conditions. What we have here is a regime where we have, for 2 weeks before the test date, 40 degrees C, 60% relative humidity controlled, so that, and the cube's the same, so that everything we test is basically at the same moisture content, same conditions. Again, this requires quite a lot of input as well to provide these facilities. This shows the specimen under load. So you can see here, we've got here 3 thermocouples on the outside. I think this is a Crossrail one. The specimen is in the machine, and this is a gas-fired furnace, controlled through Type S, which is a platinum thermocouple, quite a high standard thermocouple, to give the control on the furnace. Once it's been tested, this is from the back actually, so the unexposed face. We take cores from various locations, and the cores are then cut and split into 50 mil cylinders, and the residual strength is assessed through compression testing. So we end up with a log of the strength with depth from a distance from the exposed face. Okay, so precast linings. I mentioned that for the Crossrail specification there were two different test methods. So same fire curve, different specimen size and shape, different loading arrangement. And I think the specification, personally, the specification is dependent on the experience of the consultants employed to develop it. So the specifications are generally written by a consultant. If they've had experience, if one consultant has had experience of working with BRE, then the specification reflects the work done by BRE. If they've had experience of working with maybe TNO in Holland, it will reflect their conditions. And I think there's not a lot of logic behind it, to be honest. So this is a schematic of the furnace situation in terms of the segment testing, which is much more complex, much more expensive, and much more difficult to carry out than the work that we do. And maybe it's necessary, who knows, it's not my call. I sometimes wonder if this is actually all necessary to achieve what you want to achieve. But there we go. We can't do this. There is an alternative, which is the mountain to Mohammed principle, which is bringing the furnace to the tunnel. And there are more than one company on the continent now who offer this service, where you can actually bring the furnace up and do an in situ test, which is quite interesting. So, next steps, which is where we are now. The specification's been prepared for the fire testing of the tunnel linings for HS2. And what's notable from our point of view is the specification is applicable to all permanent concrete in tunnels and other underground structures, including sprayed concrete and precast. So I think in terms of the UK position, I think it's a good move, but there we go, I would, I guess. I think there is a need for standardisation in some... Sorry.
Just like to say, on Crossrail, when we were designing the portals, 2009 and 2010, the design manuals were still being developed, and fire was quite late coming in, and they did try to say everything had to be the same, but we ended up with things which were quite unbuildable.
Right.
In terms of the portal.
Yeah, yeah.
We then had to step back and really take a risk-based approach where when you did have a portal, the vertical elements wouldn't really develop those kinds of temperatures and see very much like your building test where you saw the columns are okay and the slabs were not.
Mm-hmm.
So, I'm not sure that moving forward for HS2 whether that's a good idea to say everything should be the same.
Yeah, I mean, there are the people who make the decisions on these, I think, need to consider a whole load of factors. And there's a lot of maybe modelling work that can go into making decisions on the specification. But I think things like, for instance, things like the choice of the fire exposure. It's quite easy for somebody to say, right, okay, we've got to test everything to the RWS curve. Now, I know from the work that I've been involved with for many, many years that there won't be a difference in performance between the Eureka and the RWS curve in terms of spalling. So if that's the reason, I think you need to think a little more closely about it. But yeah, it's...
Well, I mean, I was going to say for that, on immersed tunnels, which is a bit threshold, and they do ask for the RWS curve, if you have explosive spalling, but then you have progressive spalling,
Mm-hmm.
I was keen maybe I can catch up with you after to see, there's very little guidance on that and trying to estimate that. You have sustained loading because it's underwater, pretty much like tunnels.
Sure.
But thicker sections.
Mm.
So, yeah.
Okay, fine. I'm nearly there, actually, so we can discuss in some more detail, I think. So, yeah, I think there is some room for standardised procedures, maybe general standardised procedures with some options. But I think you need flexibility because the conditions in tunnels are different from tunnel to tunnel, from location to location, depending on the fire load, depending on the conditions. So I think, yeah, you need the flexibility. So the Crossrail specification, the current HS2 specification could provide a useful starting point to specifying a fire test and assessment methodology which is robust and does not impose an unreasonable financial burden on contractors. And I think that also needs to be taken into the account in the equation. And I think that's probably it. Okay? Thank you very much.
Come over, Tom. Tom, I'd like to thank you for a very succinct and easily understandable talk.
Thank you.
I had my own eureka moment. I now understand what a eureka curve is. So we'll open up the floor to questions. If you could give your name and who you work for, please. We kind of had all the questions in the presentation. Here we go, Rosa.
Rosa Diez, McDonald. You were talking about the Eureka curve, right? And we as designers find it difficult to design to the Eureka curve, and particularly with the comments from fire engineers who consider that the Eureka curve does not represent the fires that we could have in railway tunnels, for instance, because you no longer have hydrocarbons inside a railway tunnel. So what are your views on using something different, or is there anything else or any other fire exposure that could be used? Because I think clients are reluctant to use any other because you could potentially apply a project-related curve, but nobody wants to test it, right?
Well, I think personally, where there's justification, then if you have the justification, if you've done the analysis and you your design curve is something other than the Eureka curve, you are quite entitled to use that as the design criteria, but you need to justify it, that's all. So it could be, in some cases, it could be a standard fire curve, which would be less severe than the Eureka curve. In some cases, it could be, for instance, the Eureka curve, but instead of going for 60 minutes, you go for 30 minutes. That's a potential, but you need justification, I think. I mean, I'll test anything.
Yeah, but is there any research or testing that is, let's say, being undertaken to provide a more realistic fire exposure curve?
I think most of it's done in terms of modelling because it's very, very expensive to do research into large-scale tunnel fires, but there have been a number of large-scale tunnel fires, and I think that's part of the reason why we've ended up with the Eureka curve in the first place. So it is related for hydrocarbon fires. I think it is fairly representative. But yeah, most of the work is done in terms of FDS modelling, by and large.
Neil?
GZ Consultants, formerly TfL. We, in LU, on an underground, we ended up specifying 1 kilogram per metre cube of polypropylene fibres as being appropriate based on the testing that was done, I think, for channel tunnel railing.
Okay.
Is there an opportunity to reduce that? Or is that really just about the appropriate number?
It's a very, very difficult question to answer. I don't think there is a number. I don't know if you're familiar with the fire part of Eurocode 2, the concrete code. In that, it specifies there should be, I think, at least 3 kilograms per metre cube. So you're well below that. I always thought that was a mistake because, as I think I said during the presentation, what you want is you want the minimum content that will give you the performance you require. And that will vary from condition to condition, depending on your mix design, depending on the fire exposure. So in some ways, the optimum can only be decided by, probably by testing.
So how did the 3 kilograms get arrived at? Was that because that was the number that was used for the tests?
Yeah, in part, yes. And that was written in, I think the Eurocode 2 was out in 2005, but the work that went into that was done before we did the testing at Cardington. It's difficult. If you say a number, somebody will pin it on you. But,
I understand that.
I would say, in general, the 3 kilograms is too high.
Yeah.
So, yeah, I think... but I'm not sure there's too much scope to reduce it much below 1 kg.
No, and that's kind of where my feeling was. But, and that's the point of the question, really, because the testing is the expensive bit.
Yes.
If we've arrived at a number which we're relatively comfortable with based on testing.
I would say, I'm advertising myself here, I guess, but I would say that if you're looking to optimise the dosage, you don't need to go through the full loading test. You don't need to do the panels of the size they are. You could probably do some very good work in terms of optimisation on quite small panels, just expose them to the same fire curve, which would be cheaper and easier. And we've done that for several clients in the past, but I'm not a marketing person. I'm not here to sell myself, to be honest.
That kind of tells me what I thought is that we go to a lot of expense to test things. And we usually do it when it's a very big project where it's probably most cost effective. But there's always the little client who wants something special, and it's trying to advise them that this isn't the right way to, not to do full-scale tests. Or
Yeah. I mean, you can get a lot of information out of fairly small-scale tests, but it's still it costs money. It's
Thank you.
There we go.
Jovi Nava, currently on a mini retirement. Just coming back to the question of 1, 2, or 3 kilograms meter cubed, I mean, using the guidance in the codes, you can looking at the covers you have, etc., come up with it. And yes, you end up with 3 kilograms. But then I think, again, we took an approach on Crossrail. I don't know what we ended up with in the end, because I left once the design was finished. Perhaps you can tell us. It was then a case of what about buildability, affordability, and actually end product. So I think we settled on 2. That was what I think we settled on, 2, yeah. And yes, you can test panels and things. You've shown us the difficulty in testing. I'm particularly interested to know, when we were trying to do some things for the technical tenders for Fehmarnbelt, where they did ask for the RWS curve and you had thick sections, and for sustainability and for other reasons, you had a lot of cement replacement, which meant, in the end of the day, even if you didn't start off with high-strength concrete, you're going to end up with high-strength concrete, right? And a lot of people don't think about that in the end you will have high-strength concrete. And one of the things we found very difficult was to find any curves that we could use to model. So we needed curves to see when spalling would happen, how much would it be, how much would it be affected, not just by strength, but also by aggregate type. And all that was available were these secret curves that were, I don't know if you're aware of them, that were done by 2 consultants that I won't name. Right. We were one of them, so we had access to them, to try and sort of predict were these sections that we've provided thick enough and were they going to survive this ridiculous 4-hour fire. So I came here today to hope that you could tell us that these curves are now available.
Right, okay. I've seen many attempts to predict spalling, to predict depths, to predict rate of spalling. I don't believe any of them personally. There are so many parameters that influence spalling of concrete, and you can do 2 identical tests where one panel doesn't spall and the other one spalls extensively. It's a very, very difficult phenomena to model numerically. Very, very difficult. Right.
So Charles, if you'd...
Hi Tom, long time no see.
All right, Charles.
Name and allegiance, Charles.
Do what?
Name and allegiance.
Oh, Charles Allen, independent consultant. Tom, EC2, I have lots of issues with EC2, in particular the fire spalling, anti-spalling. I think it's actually 2 kilos.
I think it's... Okay,
anyway, whether it's 2 or whether it's 3,
yeah.
it just says
Right.
2 kilos or 3 kilos of polypropylene fibres. That means you could actually use 1 fibre per cubic metre that weighed 2 or 3 kilograms. It's absolute nonsense.
Yeah.
On the Channel Tunnel, as Neil well knows, on CTRL we use 1 kilo, but that was less than 32 microns diameter. Now you can get the polypropylene fibres down to, I think it's 12 microns diameter. And you're much better off with 1 kilo of that because you end up with more surface area than with 2 kilos of something that was, say, 32. So this is one of my great bugbears with EC2.
Yeah, I mean, I wouldn't be so concerned. I was supposed to go to Paris this week, so I work on the project team updating fire part of EC2, and it's going to be completely revised.
It needs it.
Well, it was written at a time when the concrete industry in general didn't really deal too much with fire. As far as they were concerned, you just picked a cover, you picked a dimension, that was it. That was your fire engineering, and you're done, you're sorted. Since then, there's been a lot of work done on the continent and in the UK, and I think we're in a better position to offer more logical guidance than there is in the current version. And there'll be a new section on spalling.
Yeah, one of the issues, because I did some work for a couple of contractors on Crossrail, low-strength concrete with 2 kilos of polypropylene fibre, because a lot of air was entrained because of the surfactant on the fibres. And number 2, the mesh of the volume and mesh of fibres within the concrete did not allow you to vibrate out the air. No. So you ended up with lower strength. Mm.
Yeah. Steve Parker, if you wait.
Steve Parker, consultant, currently on LTC. Ivan, you and I were both on C300 Crossrail. As I recall, it was 1 or just over 1 kilo we ended up with. But the problem we had with testing was the 2 and the 3 kilograms. I remember poor Bob Wagstaff complaining at Autocom that they couldn't mix it. We had problems with 3 and above. You couldn't mix the product.
It becomes impractical.
So we ended
after,
up with 1.2, as I recall, if anybody got a better figure. Yeah, 1 kilo for Crossrail C300.
Middle.
Hello, I'm Asil from Warwick, studying MSc in Tunneling and Underground Space. So I just had this question to confirm, like regarding the kilos and the discussion of that fiber. So basically the fibers are there to provide the air an outlet to go out of the concrete to prevent spalling, right?
Yes.
So would you then suggest some volumetric system of dosing that in that case, or whether the length of the fiber does matter in that case and the orientation, does it?
I think it does, yeah. I think there's the dispersal of the fibres matters a lot. The ratio of the surface area to volume ratio matters. So you can get different performance from the same dosage. So I think it's a complicated situation. I'm not in the business of supplying guidance for people in this area. What we do is we carry out an assessment of performance. I think if you need to consider it, then you need to test it.
Just one last question. In case of an RCC structure and an FNFRC structure, where you mix in the fibers, definitely the FRC would be more fire resistant, right, in that case?
Right.
In case of RCC and fiber reinforced concrete.
Right. Okay, so what's the question?
The question is like, which is better to use in this case? Where you are incorporating fibers in that.
I don't know, is the answer.
Okay, we're going to, the bar is open at 7 o'clock, so John back, John Greenough.
John Greenough, Becker. We supply fibres. Firstly, the micro polypropylene, because there are 2 types, micro polypropylene are for fire. And Charles is quite right. You can either have 2 or 3 kilos of a 32 micron or above polypropylene fibre, or you can have maybe 1 kilo of a fibre which is only 18 micron. And the difference in fibre volume is literally millions per kilo, and certainly per cubic metre, whether it's in sprayed concrete or in precast concrete or in cast or shuttered concrete. Most of your early slides from C2RL, I believe that testing was done at Boreham Wood at the Loss Prevention Council.
No.
Well, it certainly was, because I was up there with Peter Shopworth.
It wasn't. It was done at Garston in Halsey in the structures lab by me.
No, we did work at Boreham Wood. Because I took the photographs and I gave them to Peter Shopworth.
Those photographs are mine.
Yeah, well, yeah, but what I've seen is virtually identical to what we photographed at Boreham Wood.
Right.
So it concurs exactly with what you're saying. But the work at Boreham Wood was all done with steel fibres as well as polypropylene. And the projects that you've mentioned, Crossrail, etc., the bulk of that work was all with steel fibres. So the question would be, have you done any work to compare the blend of steel fibres and polypropylene fibres in concrete with fire, and let's say polypropylene fibres with traditional steel cages?
We've done, I mean, all the work we've done in this area has been commercial work. So we've tested conventionally reinforced linings. We've tested steel fibre linings. Steel fibres, to my knowledge, don't really give you any performance in terms of fire.
True.
So
True.
What we normally are looking at is steel fibre reinforced with polypropylene fibres. That's a normal case in terms of most of the situations we've been asked to test. Sometimes conventionally reinforced, but yeah, in general it's steel fibres and polypropylene fibres.
Yeah, the thing with using the steel fibres is the crack width limit. So they do actually control the cracking with greater effect. Where on the first channel tunnel fire, I think the explosive spalling was the thermal conduit that the steel cages provided. Because when we did the work with Peter, when we cored down, we saw the loss of micro polypropylene was around 4 inches or 10 to 11 centimetres. Under the microscope, you saw the micro voids. So again, it's that's why I'm curious about the traditional rebar cages and that work.
Right, okay. Was that Peter Shuttleworth?
Yeah, Peter
Right, okay,
Shuttleworth
yeah.
and I think Eddie Woods.
Yeah, those tests were done in our lab. It's for CTRL.
All right, no worries. Thank you.
With one more question. This side, Jed.
Thank you. John Murphy, retired. Can I just widen the questions out a bit? We've been talking a lot about concrete. There are other things in tunnels that get hot, notably the road surface. I think the people who are looking at the duplication of the Blackwall Tunnel are interested in what will happen with a tarmac road if it gets really hot. I don't know if you've got any commentary on that. I know it's a bit off what we've been talking about. And the other thing is there are things like doors, escape doors in between one tunnel and another tunnel. If they get really hot, there's a bit of a problem there. So I know it's a bit off the subject of what we've been talking about, but I think those two things are worth a bit of thought.
Absolutely, yeah. I mean, fire has impacts everywhere, and the most important impacts are the ones on human beings. They tend to be the ones I don't get involved in. So things like means of escape and early warnings and early things like toxicity and issues like that are far too complex for me to deal with. I deal with structural fire engineering issues, which is why it tends to be steel, concrete elements. But yeah, there are many areas in which fire has an impact on tunnel performance. So
I'd like to conclude at that because we have arranged for the bar to be a little bit earlier because Tom's talk was half an hour, not so many questions. But perhaps you could carry on the questions at the bar or sausage and chips. But I've got one question for the specifiers in the room, the designers, the consultants. That why do we as contractors have to cast segments and then transport them all the way across to Holland or Germany and get them tested at great risk in these very fancy ovens when we can go to people like Tom in the UK and just do the same thing with models, with smaller panels. Because by specifying these great big ovens in East Germany and Holland, we are exposing the client to quite considerable time risk. So perhaps if you could thank Tom in the usual way, please. So if you could have the chair slides, please. So 2nd of April, introduction to tunnel ventilation, young members, textbook talk. Sorry, I have to ad-lib these because they've just been dropped in without me realising it. So second, where is that? Where's the talk? Here. There we go, ICE, 2nd of April. Now, hot off the press. We have been affected by travel bans, and we are backfilling spaces. So there's a change. Thursday, the 16th of April, we've now got a speaker, Tideway West, Putney Worksite. Tremendous job, pipe jacking, and a great success story. Tom Brown speaking from B&B, Wardenburg and Tideway. And just as a flavour of what a great job it is, here's a photograph of them taking the machine at Putney a couple of weeks ago. So a good one and a view from site talk, very current. And then another TBM for beginners, but delivered by BASAF, Friday the 24th of April, location Rochester in Kent. I assume there's a better location in Rochester as their divot because rather struggle to find it, but I guess you go onto the contact Divot, he'll tell you whereabouts in Rochester it is if you want to go. 14th of May, we have ideas to fill that slot. We were getting a talk on the Sydney Metro, but the speaker has had to pull out because of travel arrangements, and he was trying to tie that into the World Tunnelling Conference, which is also being postponed. So we're still looking for speakers. We've got ideas, but if you have any ideas, see John Corcoran, who will no doubt be in the bar later on. Another young members, 11th of June, John Davis, joint lecture with the Engineering Geologists Young Members Group, title to be announced. There we go. So BTS dinner, still very much going ahead. 1st of May is filling up fast. And indeed, bookings are up on last year at the moment. But do remember that 1st of May date, it's a change date from the normal. The team have been busy selecting the menu, and the menu is now available on the website. It was a hard job, this. It was a hard lunch. Yeah. What we do for you. And this is the table plan available on the website. Green is still available, but we are up on bookings already, and it's selling out quickly. Warwick University, we're getting a steady filling of places, much further on in the future, and already bookings are up on last year, 6th to 10th of July, Warwick University. And now, on to Ken's dashboard. This is a heck of a lot better than some of the graphs we've been looking at in the news at the moment. But if you look, we've had a steady increase in stories, and we've had a steady increase in photographs. But as Ken will point out to you, we are a little bit low on photographs at the moment. So if you've got good photographs, get them sent in. This is as much as pictures as people. But it's been a tremendous effort over the last month. We've contacted individually 327 personal contacts, and we've now got 250 stories. So we've surpassed Ken's target times 2, I think. And in fact, we've had more than 250 stories, Ken, have we? Where's Ken? How many have we got now? 253. And how many do you think we're going to get? Probably 300. So Ken's original target was 200. He then realised we were going to beat that, so he lifted it to 250, and we've beaten that. So staggering. And I've read a lot of those stories. Everyone is a winner. It's fantastic. And we've got a good problem, because just going through the numbers as a reminder, we had a pamphlet in December of stories. In January we had a booklet. In February, you'll remember we had half a book, and blown at me now, we've got 3 books. But that is a good problem to have. We've got 220 pages in this book, so we're looking at 88 to 110,000 words. But we've actually got, or 250 stories, 300 and 450 words. Yeah, you get the third. But we've actually got, at the moment, 253 stories, 1,100 words each. So we've got 275,000 words and more to come. Have you counted all these words, Ken? Everyone's a winner. So the editors clearly have a job to do. We've got to get those 3 books down to 1. So look, there's a huge thanks to all who have contributed. But please accept that your contribution has to be trimmed down. We don't want you to rewrite the contributions. The publisher has told us that the difficult thing is getting all that raw material in. We've got that all that in. And the editorial team now is going to work and look at the book as the overall and all those stories and draw out the bits that are good and some of the duplication out. So split the chaff from the wheat or whatever it is. And when we've edited the stories down, we will be contacting all writers to ensure that the way we've edited the story meets with your acceptance. But still, and that's going to take quite a few months to do. But still, anyone who wants to write a story, get it in. And Ken's particularly keen on short ones that can be squeezed in. So we have stories from miners. Well, you can look at... Now, there's a prize here for... now, let me say, we are getting some stories from electricians, so we are going to fill that slot. But there's a prize there to spot the obvious profession who have not written a story. And the clue is in the middle column, one up from the bottom. If you put a word in front of that word, you'll come to a quick conclusion as to which profession is missing. And what do you think the likelihood of getting a story from that profession is? But there you go. If you know any members of that profession who want to write a story, then Ken would welcome it. So the next steps, the stories have been divided into chapters. The editorial team will take one chapter at a time, produce a rough layout, identify gaps, and make arrangements to fill those gaps. We will be providing all contributors and all members with a monthly update, whether it be here or by email. We're still feeling a way to doing that. So Ken's programme, the book layout largely complete. We've passed the first phase of collecting the raw material. We're now going into the editing stage. The book layout we're hoping to be largely complete by September 2020. The editorial appendices, facts, checks, illustrations by November 20. Prepare for printing December 20. Print in China. Yeah. Dream on, Ken. And ship to the UK 3 months. But Ken has got 3 months up his shirt by printing in Europe. So we are very much on target for publication to meet our 50th anniversary in March 2021. So watch out for those monthly updates and make sure they don't go straight into your junk mail. There's a lot of work to do. Ken's very keen on seeking volunteers. See him in the bar, or John Corcoran or Anita Wu in the bar, and they'll tell you more about what can be done in volunteering. And it's tremendous. These stories are fantastic, and I've certainly enjoyed reading the ones that I've had an opportunity to read, and very much looking forward to reading the book. But now I think we've got to move on to pestering you for sponsorship. So feel that you may be targeted over the coming months for sponsorship. We've already had one go at getting some sponsorship in, but now that we see that the book is going to happen, we're going to go out there and start getting sponsorship in, so that we can reduce the cost of the book to members to a price that even you will find affordable. So finally, I'd like to thank the sponsors this evening. BRE for sponsoring the bar. Thanks, Tom.
Neil.
And Neil. And OTB Concrete, Charles, for sponsoring the sausage and chips. Please enjoy the hospitality of both. Thank you very much. The bar is open.